Hello everyone. In this video, we are going to talk about forced vibration of single-DOF system, but as opposed to my previous video where the force was the reason for external excitation, this time the support displacement or the ground displacement is the reason. So let's say you have a mass and this mass is connected with like these two half springs, right? Or these two springs and this damper to the ground, so still mass spring damper system, but you don't apply a force to M, but this ground that is underneath the object, it is shaking, it's movable. You can give it this motion Y, and this motion Y is under your control. Well, when Y starts to move and X has not moved, what's going to happen? These springs and the dampers, they start changing length and getting a difference in velocities in the two ends. So they start applying forces. As soon as they start applying force to both ends, they are going to make this force M go up, and then that's where the X motion starts. And then the difference between the X and Y, because they are not in phase, the difference between X and Y is the cause of oscillation for mass M. So we want to see how we can formulate this problem, and we're going to see a couple of relevant problems to this topic. So first thing is, if you look at the FBD of the object, clearly if you look at the mass and again you measure X from the static equilibrium, so mg is not included, the forces from both of the springs, if you combine them, it is going to be K times the difference between the displacements on the two sides. So if we say Y is bigger than X, the force upward is going to be K times Y minus X, and the damper force is going to be C times Y dot minus X dot. Okay? So if you write the equation of motion along the vertical direction for object M, it is going to be mx double dot equals, and please pay attention, this x is not the traditional x. This x here is the vertical displacement. If you don't like that notation, call it something else. Call it, I don't know, capital Y or something. But actually capital Y is already reserved for something, so call it another variable. But here x is vertical, so pay attention. So mx double dot in the vertical direction equals sum of the forces. What are the forces? Ky minus x plus c y dot minus x dot, which are exactly these two. If you just apply a negative, so you make it like this, correct? Then that's exactly these two. And so that's the equation of motion for this object. Now here we introduce the relative position between x and y. So x minus y, we call it z, right? And so if we write these equations in terms of z, so this is z dot, right? And from here, if you take double derivative, you get z double dot equals x double dot minus y double dot. And if you take this y double dot to the other side, you see that this x double dot on the left side is going to be z double dot plus y double dot. Okay, so that is going to go right there. So you will get mz double dot plus my double dot, correct? So this term becomes mz double dot plus my double dot equals negative kz negative cz dot. And then if you bring these two negative terms to this side and take this y double dot to the other side, this is going to be your governing ODE for relative displacement z. Now the y here, this y motion, is given as basically capital Y times sine omega t. So although there is support displacement and it's under your control, here to match the previous formulation for external force that was harmonic, we also again assume here that the basically support displacement is also harmonic. Now many times this is not really the case, okay, but in this case, again, just to match the previous notation, and that is kind of one of the simplest kind of external forces or external displacement, we go with harmonic. So if you take two-time derivatives, because we need y double dot, you know that y double dot here is going to be negative capital Y omega squared sine of omega t. And since here you have negative my double dot, you are going to get positive, right? So that is going to go there. You're going to get positive m omega squared y sine omega t. Okay, so that is your differential equation. On the left, you have this second order linear ODE, the left side of it, and on the right side, it's not equal to 0. It's a non-homogeneous ODE, and I have a sine function. So very similar to the external force that was harmonic, you expect the Z solution here to be with some magnitude capital Z, okay? The same frequency and with some phase shift, which here we call it phi. So this is going to be what? This is going to be your Z solution. The only thing is, what is phi? What is capital Z? And if you look at this problem against the one that we had with the external force, let me go back to it for a second so you can see it. There we go. Look here. This is exactly similar to this one. The only difference is Z is replaced by X here, and this F naught in our problem is M omega squared capital Y. The rest of it is exactly the same. So these two formulas that we had for magnitude of X and for angle, these guys, I can use them as long as I replace F naught with this guy here, okay? And X with Z, that's all it is. So here I'm going to use exactly those. And so this is going to be my magnitude Z, and this is going to be my what? My tangent of phi. The phase will not change, but this one does, and here this one is going to replace F naught for you. So this is the solution for relative displacement. But remember, the ultimate goal is to find the displacement of the mass, the absolute position x, not the relative between m and y. Okay, so we need to come back here, and now that we figured out z and y is already given to us, we add z and y together to get what? To get my x. So x equals z plus y, where z is a harmonic with frequency omega, with magnitude z, and with phase negative phi. Y is, there is no extra phase to it, and the magnitude of it is y. So I need to add these two together, and if I do that and simplify it from here, if I call this x to be magnitude x and then sine of omega t, correct? And then minus psi, from here I should be able to find this magnitude x and this angle psi, the phase psi, in terms of what? In terms of z, y, omega, and psi also can be similar to phi, because remember, z and phi are already known. So if I replace them right here, I should be able to find x and psi directly in terms of capital Y and omega. And this is what I have on the right-hand side, as you can see. I can find magnitude x over magnitude y. It is going to be this function. And I can find tangent of psi, and that is going to be this function. There we go. So now what? Now I got the magnitude of my response, and I got the angle of the response. And I can plot them again. So I can plot this magnitude x over y versus omega over omega n. And again, this omega n here is square root k over m. And the zeta here, remember, that is c over 2 square root km, or c critical. So the definition of omega n and zeta is exactly the same as before. So if you plot that, you're going to see again for zero damping in the system, you are going to have an infinite resonance right at omega equal omega n. You see the magnitude of x goes to infinity, and then the bigger the zeta becomes, the bigger the damping becomes, the smaller the resonance is going to be, the magnitude of it, and the frequency of it is shifting to the left. Very similar, except the formula for omega r and mr in this function is going to be different, because if you look at it, the denominator of this is just like what we had up here. That's exactly this one. But the numerator of it is not a constant term. The numerator of it also depends on omega. Okay? So finding the optimum point of this or maximum point of that and plugging it back, omega r and mr that I had in my previous lecture, they have different formula for this case. Also, if you look at your psi, but the behavior is the same. I mean, at the beginning and at the end. At the beginning, all of the curves meet at magnitude of 1, because you can see here, if I go into this function and plug in omega of 0, what would you get? So if I go ahead and plug in omega of 0 here, or omega of 0, so I get what? I get k squared over k squared under square root, so I get a 1, so they all meet at 1 at omega of 0. And when omega goes to infinity, because the order of the numerator is omega squared and the order of denominator is omega to the 4, the whole thing goes to 0. So all of this curve will converge to 0 when omega becomes very large, okay? And they all have some resonance up to some zeta, not all zeta. Well, actually, if you look here, it seems like all zeta up to 1, they have resonance. Even 1 has a resonance. I mean, if you look at here, this is zeta of 1. Even 1 has resonance. If you remember in the previous video, when the force was involved, you only had zeta up to some value. After that, there was no resonance. And if you remember, that limit was 1 over square root 3 or square root 2 or 0.707. So zeta had to be less than or equal this in order to have any resonance or any peak. Above that, there will be no resonance. But for this case, it seems like even for zeta of 1, as you can see, there is a peak. So it seems like this case has no limitation. On zeta up to 1, at least, for sure. So the formulas, as I said, for these guys are different. If you want for practice, you can take the derivative of this x over y, take the derivative of that with respect to omega, set it to 0, and solve for it. The solution is going to be omega r. Then plug it back into it, and that should give you mr. But I don't want to go that far in this video. Just leave it up to you for a practice. Now, if you look at the angles at omega of 0, of course, tangent of psi is going to be 0, so all meet at 0. When omega goes to infinity, what happens? When omega goes to infinity, the order of numerator, if you look at it, is bigger than denominator, because this is order 3, the denominator is order 2. So the whole thing will go to infinity when omega goes to infinity. So tangent of psi is infinity, so psi should go to pi over 2 actually, as opposed to the other plot where they all converge to 180. In this case, you see as angle gets bigger and bigger, they are all converging to 90 degrees. So you see they're all coming down and they're all converging to 90 degrees when omega becomes very large. Okay? And is there a common point in all of them? Somewhere in the middle. Well, for instance, if omega over omega n equals 1, would you see a common point? Well, if omega equals omega n, this guy will go to 0, okay? For sure. And here, you're going to get mc omega n cubed. Here, you're going to get c squared over omega n squared. So, it does not look like they all will exactly fall on the same number for omega equal omega n. And if you see, kind of, they have different points, as opposed to the previous one where, as I said, they all meet at this point, omega of 1 and phase of 90 degrees. And when omega becomes very big, they all converge to 180. So although these two graphs are quite a bit similar, but not exactly, okay? So just keep that in mind. They are not exactly the same when the support has motion. Okay, now that we have seen the base for this, I want to go over a couple of examples for you. One is basically a real life example. Let's say you are driving over the road and the road has displacement on it. The road is not flat. There are ups and downs. Let's say a road that is not well maintained. And basically this road, the profile of the road is kind of a harmonic function. So here, the y, which is your vertical displacement of the road from its base, from its flat base, y, as I said, is a harmonic function where the wavelength of it is L. So here, this is a distance. This is not time axis, okay? This is x-axis. This is the profile of the road. So you know, for a wave, the distance from where the wave starts to another time that the wave repeats itself, this distance is called the wavelength. Okay, if it was versus time, you would call it period. But this is versus position, so that L is the wavelength of your sine wave. The distance that the car travels, the simple 1-DOF car model, travels from the start point is v times t, where v is the horizontal speed of the car, t is the time. If x here represents the vertical displacement of the center of the tire, y represents the profile of the road, and all you do is to connect the tire to the basically passenger part of the car by simple springs. So all of your suspension of the car is a simple spring. There is no shock absorber, and this is very, very simple car model. And the weight of the car is W. What is it that you need to find? You want to find what is the most unfavorable speed. You probably all experience that when you go on a road that has bumps. Depending on how fast you pass the bumps, you're going to get different amount of up and down vibrations. This up and down vibration in a car is called ride. Okay, this degree of freedom is called ride. So we want to see which one of these V's that you can pass the bump will give you the worst kind of ride, the biggest basically amplitude x for the ride, given all of these parameters. So first thing is, of course, you have to write the governing equation of the system. Now in this case, clearly, if you look at this W and again measure the displacement x from static equilibrium, so mg is not included, the only force is coming from the difference between y and x, so it is ky minus x. And so, since x is in this direction, you're going to get mx double dot equals ky minus x, correct? So this negative kx, you bring it to this side, and ky you keep to the other side, and so you get this governing differential equation for the system. Now y here, the profile of the road, as we said, is harmonic. So it's some magnitude times some frequency, sine of some frequency. And why sine and not cosine? Because you see at x, at the beginning, it starts at 0. So this is a sine profile, not a cosine. So it's a sine function. The magnitude of it is called y naught. So the magnitude of it is y naught. And what is the frequency of it? So it is something like y naught sine of omega t. The question is, what is omega? If the signal was versus time, remember omega was what? Was 2 pi over t. If the signal was in time domain, but this is in frequency domain, okay? And sorry, it's in the x domain. This signal here is not sine of omega times t. Actually, it is sine of omega times x. So this function, and yeah, here that x can throw you off. So because the vertical motion is called x. So let me call this something else. This direction, let me call it something else. Let me call it r. Okay, so it is omega sine of omega times r. Okay, and this r is of type meter, is the distance. So first of all, what is r, what is omega in this case? R is the distance traveled. The distance traveled, if the speed of the car is fixed, this r can be replaced by v times t, where t is the time, v is the velocity or speed. What about omega? As I said, in the time domain, it would have been 2 pi over t, but in this distance domain, instead of t, you have to replace it with what? With L. So your actual function is going to be y naught sine of 2 pi vt over what? Over L, and this is exactly what you can see over here. Here. Look at that. So that is the profile of the road that you are exposed to at any time. Starting time of 0, the profile height is 0, and the amplitude is y naught, the velocity of u is v, the wavelength of the road is L. So now with that y, and so that is your excitation, that is your base motion, and this is your ODE. So what kind of solution would you expect? Well, because your input to the system is of this frequency, you should expect the output x to also be of the same frequency. So you see, it's also sine of 2 pi vt over L, except what? Except you have a different magnitude and a different phase. If you can find the different magnitude and phase, that's all you need to do. But remember, the system has no damping. So if I want to copy these transfer functions that I have up here, I have to remember to set the damping coefficient to 0. So I can use these guys, except I have to replace C with 0. So wherever there is a C, I can remove it. And wherever there is M, I can have it as W over G, because W is the weight here. If I do that, the magnitude is going to be x equals, or x over y naught equals what? Let's go take a look. What is it going to be if I plug in C of 0 here? If I plug in C of 0, as you can see, it is going to be square root of k squared over k minus m omega, the whole thing squared. And if I get rid of these square things with the square root, it is going to be k over k minus m omega squared, correct? So if I want to do it, my x over y naught is going to be k over k minus m omega squared. Now I divide both of numerator and denominator by k. If I do that, I get a 1 here in the numerator, and in the denominator, what do I get? In the denominator, I will get a 1 minus This m over k is 1 over omega n squared, so it's going to be omega over omega n, the whole thing squared. And that is exactly this. Here you can see that power 2 and that square root, I can get rid of it. So the magnitude is going to be 1 over 1 minus r squared, where r here is the ratio of omega over omega n. And what is omega over omega n? Well, my omega in this system is this coefficient of t, so that is my omega. Okay, this is the omega of the system, and omega n, remember, is the square root k over m. So that is this guy, and omega n is this one. So now I found magnitude of x over y as a function of this ratio r, and this is that ratio. So far so good. Now, under what condition you have the worst case scenario? Under what condition you can get resonance? Remember, the worst case scenario is a resonance, and resonance happens for a no damping system at what frequency? At where this ratio equals 1. So when this ratio r equals 1, that's the worst case scenario. So I'm gonna set this ratio equal to 1. If I set this equal to 1, that means numerator and denominator have to be the same. And if I need to solve for v, because remember I want the worst v, the most unfavorable velocity, if I simplify, this is gonna be the critical speed. So if you are riding a car and you know the wavelength of the road profile, let's say it's a bunch of bumps, and you know the k and m, and if you want this m, you can replace it by w over g. So you can replace that m by w over g, then you get L over 2 pi square root of kg over w. Okay, this is the worst speed that you want to pass those bumps. You're going to get very, very large vertical displacements. Now, in real life, of course, there is always a damping. There is always a damping. In that case, you have to use this formula. C is not 0. And you have to find the frequency that gives you the worst case scenario, and that frequency is this omega r. So you have to know for that zeta at what frequency you have the worst case scenario. So you have to find this peak point, the omega for the peak point. You have to find it. You have to have a function for it. So if you want, I can actually perform some calculations and find the omega r in this system and mr, but I would rather you do it, so it's a good practice for your calculus as well. So here is the first problem, a driving problem over some bumps and learning with what kind of speed to not pass over the bumps if you don't want to go up and down in the car a lot. So that is the first problem. Now let's go to the second problem. In the second problem, we have a pendulum. And the pendulum, originally, you know, what we learned in the past is this pivot point is fixed. So the equation of pendulum is very easy. But in this case, this support point of the pendulum is not fixed. It's actually moving in a horizontal groove. And the motion for this pivot point is given by x0, where x0 has a magnitude cap x0, and it has a harmonic component to it. So the base of the pendulum goes left and right. As a result of that, the x position of this end of the pendulum with respect to the origin, or this angle theta, will start changing as well. So what is it that we need to do? First of all, we want to find an equation, a differential equation governing x, or you can say governing theta, because these two are related to each other, where you find the magnitude of x over the magnitude of x0. You want to find that, and then you want to show that when this frequency of this base, omega, is equal to square root 2 omega n. Now, what is omega n? For a pendulum without support, remember, omega n was square root g over L. So when your excitation of the base, the frequency of that is square root 2 times this, you can find a point midway in the pendulum that does not move, because this point moves by so much forward, this point moves by so much backward. This point in the middle does not actually move from its start point, and that's why we call it a node. So node is a point that does not move at the vibration, okay, or in a what we call a mode shape. So we want to show that mode for this excitation frequency is going to be right in the middle of the pendulum. So that is a relatively rigorous problem, and I had to go through lots of math to show it to you. So let's get started. Okay, to show you how the ODE is derived here, x minus x naught equals L theta. Where does that come from? Well, remember that this distance here is L sine theta. This distance here is L cosine theta. Now here we use a small angle assumption. So sine theta is approximated by theta and cosine theta approximated by 1. So the distance, the relative distance between absolute position of pendulum and the absolute position of the base, the difference between x and x naught, is L theta. That's your first thing that you have. Now, if you take a double time derivative from this, you get x double dot minus x naught double dot equals L theta double dot. And then you can multiply both sides of it by L, so you get this relation. Okay, why did I do that? I'll show you, because I need this guy in the future. Now, to get the governing ODE, I am going to take some of the moments about this point O, but you have to pay attention that point O is not the centroid of the system. This is the centroid, and it's not even a fixed point. Okay, remember, when the pendulum base was fixed, you could take moment about the fixed point, or you could take moment about the centroid. But this point O is an arbitrary moving point. It has motion, it has acceleration. When that point is an arbitrary point, you cannot simply say some moment about O is I about O times theta double dot, okay? This equation is not going to work, because O is not a fixed point, it's not the centroid. The equation that you have to use is to say some of the moment about O, or torque about O, is equal to what? I about centroid times alpha minus R of O with respect to Cm cross MACM. This is your inertial force. That vector here is from Cm to O, so that is this vector here. That is R of O with respect to the centroid. I need to cross that vector with MACM, and this is only going to be in the K direction, as well as, of course, ICM theta double dot is going to be in the K direction out of the board. And some of the moment about point O is also going to be all about K. So everything is going to be along the K axis out of the board. Now, in this object, if you look at it, the mg is there and the pin forces. So if you take some of the moment about the pinpoint, the only force that creates any moment is mg, and not all of the mg, only mg sine theta. Remember, this is mg sine theta, and this component here is mg cosine theta. So only mg sine theta will create a moment, and since theta is counterclockwise, the moment of this is clockwise, so it's going to be negative mg sine theta times L. So that is your total moment is equal to ICM theta double dot minus R of O with respect to Cm times this. If you want to know where this formula comes from, I have a video under my playlist Dynamics where I explain that the simple relation that some moment or torque about some point P equals I about P times theta double dot, this equation, or you might call it alpha, This equation is only valid if P is a permanent fixed point or the centroid. In this case, point O is none of those. When that's not the case, you have to add an extra term and change that P to the centroid. Okay, so if you want to know that, there is a video on my channel where I talked about kinetics of rigid bodies in 2D. That's this video here. It's called Planar Equations of Motion. So if you go to time 3.1516 in this video, here is the part that I'm explaining that equation can only be valid for a permanent fixed point or center of mass, or if the point is accelerating toward or away from the center of mass. If the point is an arbitrary point, then that relation is not going to work. And here I showed this cart as an example where you have a point where you want to take moment about a moving point. And then I basically here, that's this relation here. I explained this relation, and in one of my other videos, I even proved this, why this equation is valid. So if I go back here, it says 3 important proofs of rigid body kinetics. One of them is this formula. So here, basically, as I said, I used it, and here I have explained why this formula is true. So you have to use that formula, otherwise, if you just go with some moment about O equal I about O times theta double dot, you are going to get the same equation that you got for a pendulum that was completely fixed at point O, and that is clearly wrong. So solving this problem needs a little bit extra knowledge from dynamics and a little bit more patience. Otherwise, you are going to get wrong results. So here, this is that R vector, which you see I have written it in terms of, again, L sine theta in the negative x direction, positive L cosine theta. So that is this vector here. Okay. This M, I brought it out of the integral, the cross product. And for ACM, what I did is first I calculated the position of the centroid. The position of the centroid is what? For x of it, it is x naught plus L sine theta. I add these two components together. That is going to give me my x. And then in the y direction, I go down by L cosine theta. So it's negative L cosine theta y. I took double time derivative of that. So I ended up with this by doing 2 time derivatives. That's the acceleration of the centroid. This is that R, the M came out. Okay, there should be one M here, and I get rid of that. And with it, both sides have M, so I can get rid of the M from both sides. And then the other thing is this guy here, I about centroid theta double dot. What is I about the centroid? Well, in this case, your object is like this, and all the mass is concentrated at the centroid. The rest of this bar has no mass. So I about centroid for this guy, where this is massless, is simply going to be 0. So that's why here I replace that with a 0. And when you carry out the cross product, okay, you're going to get some result. But before that, I need to use my small angle assumption. So wherever I had sine theta, I replaced it by theta. Wherever I had cosine theta, I replaced it by L. Also, if there is a term that has 2 small terms multiplied together, or a term to a power more than 1, I consider them much smaller than the rest of the terms, and I eliminated that. For instance, here, look, this is a theta, and this is a theta dot. When theta is a small, theta dot is also small. So here, this is 3 small terms multiplied together. That is much smaller than this single small term. So that term I neglect compared to everything else. The same thing goes here. This is a theta times theta double dot. These are 2 small terms multiplied. And this one is 1, but here again you have a power 2 of a small term. So all of these terms that are more than power 1 of a small term, I get rid of them. only the ones that only have one theta dot, one theta double dot, or just one theta, those are remaining, and this is what you get. Okay? Now, of course, you can get this from this equation too. If you just take x0 to the other side and take double dots, you're exactly going to get this. And since this L cosine theta is approximately L and is constant, the y double dot of the pendulum is practically 0, and that's what you can see here. If you look at the acceleration term, it's only in the I direction plus 0 times j, because both of these are 0. So if I carried out the cross product, and for sine of theta, I replace it with theta. So once I simplify and clean up everything, this is going to be my governing ODE, equation number 3. L squared theta double dot plus GL theta equals negative L x naught double dot. And x naught is the one that is a sine function. So double dot of that is also a sine function. Now, what do I do here? Now I replace this L theta double dot from equation 2. I replace it by this guy. There we go. And then the L theta also, I replace it by x minus x naught multiplied by this g. So I get gx minus x naught, and then the right hand side is whatever it was. Now, in this case, I basically keep these x terms on one side, and then if you look, this Lx double dot and this Lx double dot, these negative terms can cancel each other. The only term left is gx0. I take it to the other side and divide everything by L, and I get this one. So there we go. This is your simplified governing ODE in terms of x, because this guy was in terms of theta, and I could have solved that if I wanted to, and then add theta back here and then solve for x, but instead I replaced theta already, so when I get my ODE number 4, I can directly go for x, because that's the goal. I want to directly go for x, not for theta. Okay, I introduce omega n, as I said, as a square root g over L. If I do that, my governing ODE is going to be on the left side, is going to be this. Here, I replace that x0 with this one, and this is going to be my right hand side. So there we go. That is now my final governing ODE. Second order linear ODE with constant coefficient. The right hand side is a harmonic function. If I go for the magnitude, based on my previous knowledge, the magnitude is going to be this. Pay attention, in this system, there is no x dot term. So C in this term equals what? 0. There is no damping in the system. So if I want to get any of those formulas that I learned in the past, all I need to do is to get rid of C. Okay, so I have to get rid of C, sorry, not there, here. I have to go and get rid of C. Remember, in this this one here, I can use any of them, but I have to get rid of C. And if you simplify this, if you remember, it was basically omega n squared over omega n squared minus omega. So this is that transfer function if C is 0. Good? Where omega n is this square root g over L. So now that I got the ratio that I wanted, and I got the differential equation that I wanted, the last thing is to find the node. Now it says if you plug in omega equals square root 2 omega n. If I plug that here, this is going to be 2 omega n squared. So the denominator is going to be negative omega n squared. And simplify, you get a negative 1. So your ratio is going to be negative 1 at this frequency. And what does negative 1 mean? It means that if I draw the pendulum, if the top point moves by x0, the bottom point, so this is the top point of the pendulum, and this is that original vertical line, the bottom point of the pendulum is moving by how much? By x equal negative x naught. So my pendulum is going to be like this, where there is a point here that has not moved. Where is that? Because this is x naught and this is x naught, clearly this height h has to be equal to L over 2. That is my node, and this is the point that does not move. It happens at h equal L over 2 for this specific frequency. Of course, if I change my frequency and get the different ratio, for instance, this guy becomes negative 2x naught, then my node is going to be a different location, right? So for different omegas, as long as this ratio becomes negative, which means omega should be bigger than omega n, as long as omega is bigger than omega n, this ratio is negative, and negative means one side goes to the right, one side goes to the left, so there is always a node. Where? Based on this formula here. All I need is to use a simple trigonometry and find the location of the node. Okay, so hopefully solving these two examples and going through force vibrations with support displacement, harmonic support displacement was useful to you, and I'm going to see you in the next lecture. Thank you.